Welcome back. We are now beginning with a new topic, and this new topic is about a more probabilistic interpretation and approach to the machine learning and deep learning. In order to achieve this, we need to go through some background material. And some of this material deals with Monte Carlo methods, Monte Carlo Markov chains, and probabilistic models for deep learning. We're also going to encounter, for those of you who have taken a degree in physics or studying physics, you may have encountered topics like the partition function, and this is going to lead to a topic which is called Boltzmann machines, and we will later move into what are called variational autoencoders and also generative adversarial networks. The material here will also serve as a stepping stone towards material which we will cover after the Easter break, which deals then essentially with Gaussian processes and Bayesian statistics. And that will be the final topic which we cover in this course here. So the topic now is essentially covered by Goodfellow's chapters 16 and 18. And we need to revisit some of this material because it lays the foundation for what is going to come later. So it's going to be a lecture today, will be a mix between some material which many of you have seen before and new material which will link us with what are called Boltzmann machines. Now, many of the things which we're going to do now in the coming lectures till the end of the semester can be represented in a graphical way by something which is called directed or undirected graphs. We will not use this kind of graphical way of setting up things, but it's useful to visualize what is going to come. So what I'm going to do now is to switch swiftly over to the whiteboard, and we're going to set up the type of models which we're going to encounter and why we are going to model these topics in a specific way. After that, we are going to remind you a little bit about Bayesian statistics, so which many of you may have encountered. And after that, again, we are going to remind ourselves about Markov chains, and then obviously Monte Carlo Markov chains and how to simulate them. So for some of you, there are elements which you've already seen, but we are going to put them together in a kind of unity, which is the unity which is now revised in Goodfellow's et al.'s chapter 16 and 18. So I recommend you actually take a look at these chapters in the textbook. So I'm going to switch over quickly to the whiteboard and present to you some of these basic models by which we can visualize what is going to happen or what kind of theory we need to cover. So we are now in the process where we are going to bring in probabilistic modeling. So, and in order to do that, we need to explain some basic concepts. Probabilistic models. And these are often, from an overarching point of view, they are often represented in terms of graphical models. So we have something which is called a directed graph. So you could think of something happening at a time t0, and you have a probability for being in this state at time t0. Now this propagates to a time t1, and you have now a probability of t1 given t0. So the sign which you see here, this vertical sign of this bar, represents given a certain event which has happened or occurred before the next event. And then we could move on to our next event at time t2. So you could think of this as a time series. And then there's a probability for t2 given t1. Now, one of the reasons why this is important, this kind of way of setting up the problem, follows from the following simple example. Suppose you have 3 people running in a relay race. So there is a time for the first person running, which now the final time, which could be modeled with a probability pt0. And then this person actually gives the relay pin to the next person, and that person runs at a time t1, but clearly the final time of that person is obviously dictated by the time which the first person had at t0. So there is a clear dependence on the final time of participant t1, given the final time of participant at t0. And then finally, the final time t2, and the final person who takes over the relay pin from the person at t1, the final time of that person is obviously given by the probability of t2 given the time t1. So there's a chain of events here. Now, what you could do if you wanted to model this type of activities is to think that you could split these times, t0, t1, and t2. So suppose you make measurements now, the final time a person has, and that each time slot, t0, t1, and t2, is split into discrete variables with, let's say, you run over 10 minutes. So you take the time from 0 to 10 minutes, and you split that into 6-second chunks. So that means that each participant, t0, t1, and t2, can be then represented the time as a measurements with 100 possible values. Now, what we want to do next is actually to represent the probability of these times, t0, t1, and t2. So suppose now that you want to have 100 possible values for each participant. And then for each participant, then you would then have 100 times for t0, times 100 times values for t1, times 100 values for t2, but then you have to subtract 1 because you have to sum these probabilities to 1. So that's a condition on the probability. But that gives you 999,999 possible values. So that's if you want to approach the description of this system in this kind of brute force way, you will have to store almost 1 million of values. It's actually 1 million minus 1. Instead, if you now think of these conditional probabilities, so that what you would have now is a probability of pt multiplied with pt1 of t0, and then you have pt2 of t1. So this is a chain of conditional probabilities. Then the distribution over t0 requires 99 values because we have a condition that it has to be normalized to 1. And the table which defines t1 requires then another 99 values. So that means that what you end up with, another 100 values. So you end up with 99 times 100. So which means 9,900 values. And so does the table which defines t2 given t1. And in total then, if you think in terms of this chain of probabilities which are multiplied with each other, instead of you storing close to 1 million values, you end up storing less than 20,000 values. So this is an incredible saving of memory. And it means that in this case, you have actually reduced it with a factor of 50, the memory requirements. So this is one type of probability distributions and probability types of events which we will encounter. And these are often given by directed graphs. And this type of machinery here is normally often modeled with Bayesian statistics, which we will come back to in just a few moments, because we're going to define some probability quantities which we will find useful also when we look at what's called undirected graphs. So Bayesian statistics is going to be one of the ways by which we will describe this type of events. So there is a direct connection between the previous event given by a conditional probability that T1 can happen given T0. So Bayesian statistics is something which we will look at briefly today, but we are picking that up after the break. and then in connection with so-called Gaussian processes. Now, the other type of process which we often encounter is something which is normally given by undirected graphs. So this kind of graphical way of setting up things is a way by which we can visualize to a certain extent what kind of processes we are having. So in this previous case, we had a clear direction from T0 to T1 to T2. When we look at this undirected graph, there is no clear direction. So we could now think of a PT0, you have a T1 and a T2 here, and they don't need to represent time, but we link them like in this way. So there's no preferred direction. So there's a probability of PT, there's a probability of PT1, and there's a probability of PT2. Now, what you could think of now, so there is, as I said, there is no clear direction. And an example of such a situation could be a model which models a distribution of 3 different binary variables. So you could think of T0 being you and whether you are sick or not. So this is a binary case. T1 could be a friend of yours, and the friend of yours could be sick or not. And T2 is another person who is a friend of your friend, but may not be a friend of yours. And that has another probability, PT2, which is given by a binary model again, sick or not sick. So as like in the relay case example, you can now make some simplifying assumptions about the kind of interactions that can take place. So what you could assume then is that your friend and the friend of your friend do not know each other directly, or assume you could think even of T1 being a co-worker and T2 being a roommate of the co-worker. So you could assume that one of the persons here, like T0, does not know T2, but T1 knows T2 and T1 also knows T0. And then if you assume that not everybody knows everybody, it's very unlikely that one of them will give the other one an infection, such as a cold. So in this case, we are modeling you having a cold or not having a cold. And you could think of such an event as being so rare that's acceptable not to model it. However, it's reasonable to assume that either of them could give you a cold, and that you could pass it on to the other one. So you can model this indirect transmission of a cold from your friend to the friend of your friend by modeling the transmission of the cold from you. So you could think of you modeling the transmission of a cold from T0 to T1, and that T1 could transfer it to T2, but then T2 could transfer the cold to T1, which again in turn could transfer it to T0. And these kind of indirect transitions or transmissions, they are normally represented by these undirected graphs. So in this case, for instance, it's not easy for you to cause this person T2 to get sick, in case because T1 would also, or the person T1 would also have to get sick. So the likelihood for you transmitting a cold from T0 to T2 is assumed to be pretty small. And this type of modeling is something which normally leads to this kind of undirected graphs, because there's not a clear direction of who gets the cold from whom. But you could model this in terms of the different probabilities that T2 has a cold, and there's a probability that if T2, the person which T0 doesn't know, may transfer a cold to T1, and then T1 may transfer a cold to T0. And in this kind of type of modeling, we often then deal with undirected graphs. So there are 2 types of basic modeling, which we are going to look at. And this type of modeling here is normally modeled in terms of a Markov chain. plus Monte Carlo sampling. And this is normally shortened to Markov-Chain Monte Carlo, or just MC squared. So I hope you see the basic difference with the two approaches. One, the Bayesian statistics can actually reduce the dimensionality considerably for the type of problem we're dealing with. And then we have the other case, which are these so-called undirected graphs, where we don't have a clear direction in the way things evolve. And this is normally modeled by Monte Carlo methods. So we have the Monte Carlo Markov-Chain sampling type, which we are going to put most of the focus on first. And then after we're done with that, we are going back to the Bayesian statistics. Now, there are also two ways of modeling statistics and these kind of processes. One is called the Las Vegas basic algorithms, which always returns a precise probability, or gives actually the correct answer. And these algorithms consume a random amount of resources, usually memory or time. In contrast, we have the Monte Carlo algorithms, which return answers with a random amount of error. And the amount of error can typically be reduced by expending more resources, which means usually more runtime and memory. But the Monte Carlo algorithms normally provides an approximate answer. And we will essentially stay, from all practical purposes, we will stay with the Monte Carlo approaches, which are really tailored to a multidimensional type of data. So this is a kind of overarching view on what we are going to look at now. And what comes now is a set of technicalities which we need to go through. And this is going to lead us, this basic setup on Monte Carlo Markov chains. This is a topic we need to revisit. We need to revisit a little bit about Bayesian statistics, which comes later, but we are going to use some of the results from statistics and Bayesian statistics in order to set up the probability distributions which we need. And the next step which we need to set up is a probability model. And we are going to deal with what are called energy-based models. So the probability model which we will have is now going to be given by a probability of an event X. So this is a total probability. And this contains the probability function, which is not normalized, divided by a normalization factor, which we call Z. And this links with the statistical mechanics and statistical physics, for those of you who are familiar with that. So Z is a normalization constant. And it's normally, if we have a continuous distribution, this is actually a quantity which is going to be almost impossible to calculate because it's a multidimensional integral. So this is a normalization factor for the probability distribution. And you will encounter this often as the partition function. And this is a name which we have taken from statistical physics because it deals with the way you can distribute the energies in a specific system. And this is going to lead, this kind of concept is going to lead us to a so-called energy-based model and the Boltzmann distribution as a way to model the system. So I'm going to try to explain this kind of overarching ideas first, and then we go back and look at the various calculational details. So this is the probability, and this Z is then a normalization integral over P of X of D of X, and X is now a variable which can represent a multidimensional set of variables. So it's not limited to just a scalar, but this could be a two-dimensional, three-dimensional, or a many-dimensional system. We also have made an assumption that this Z is something which is smaller than a value M, which is again smaller than infinity. So that is, it is bounded, and we can actually define this quantity here. So the partition function itself is a quantity which is going to be something which causes us some problems when it comes to reliably calculate it. Now, a common way to set up this probability distribution is to use so-called energy-based models. And this is inspired from statistical mechanics, statistical physics, energy-based models. So that means that we are going to model this using the Boltzmann distribution. So let me bring that up. So just to remind those of you who are physicists on how the Boltzmann distribution arose. So Boltzmann was actually sitting on data from observations and could actually model the decay pattern which he saw in terms of a distribution where you could now set in the energy of the system. And we are going to meet this again a little bit later when we are looking at the Bayesian statistics, because there we are going to encounter, let's say, a Gaussian distribution. And if you think back to the Maxwell-Boltzmann velocity distribution, this is something which runs like a Gaussian. If you rewrite the velocity squared, which you have in terms of the kinetic energy, you can actually rewrite that distribution, which is a Gaussian, in terms of an exponential, which runs like exp of minus, and then we have this energy as a function of this variable x, which we haven't specified yet. Now, the assumption here is that this E of x is a quantity which we have a known form for, and it's known as the energy function. So these are quantities and names which are borrowed from statistical physics. But in our case, we are going to reinterpret these in terms of parameters for a neural network. This is the closest we get to a standard neural network setup. And this is going to lead to a type of neural networks which are called Boltzmann machines. So this is known as the energy function. And we are free to model that one as we want. But we will typically model that in terms of parameters for the input layers and also for hidden layers. And there will be biases and weights which connect input layer with output layers. So we are actually free to model this function. Another thing which is important for us is that this function exp, if we look at that one, without the energy, this is always larger than 0. So this means that we have it will always result in a probability which is larger than 0 for any state x. So this is going to lead to a probability. It will be infinitesimally small, but it's a probability which is never 0, which is always larger than 0. So that means that there is always a likelihood for a specific event to take place. We are free to choose the energy function as we want, and we can tailor it so that it is specifically defined for a certain learning problem. We can also have discrete events, which is the most common case, because in many cases we are not able to model continuous variables, obviously, in most cases. So we can have a discrete probability. And in that case, we would have a z function, which is now given as a sum over the domain of possible events which we have. And this is a normalization factor, which now runs like minus e as a function of this x of j. And that means that the probability of finding the system in a specific state, I, which is now indicated by this variable x of I, is given by the exponential here. And then we have minus e of x of I divided by the normalization factor, Z. So when we are going to optimize learning algorithms that involve energy-based models, then it's actually common not to optimize this probability, but it's actually common to optimize the logarithm of that probability. So this E of X, we can look at a simple example. This can now be written out in terms of a neural network, the parameters of that. So we could think of this as being given by a bias parameter, B. This is a vector, and it has X of I. So X of I now can represent a vector. It could be just a scalar. So we don't need to specify it, but it would be clear from the context of what this quantity is going to look like. And then we are going to have a hidden layer, which also has its own bias, and we indicate that one an H of I. And finally, we have a connection between the hidden layer and this input layer, or visible layer, that's often called in connection with Boltzmann machines. And we will then have an X of I T, and then this is multiplied with a weight matrix, and it's multiplied with a hidden layer here. So graphically, if we now go back to this graphical representation, you could now think of 4 different nodes for the hidden layer. So you have H1, H2, H3, and H4. And then you have an input layer or visible layer. So we call this the hidden layer. And we can call this the visible. So some people replace X with V, visible or input layer. So we have the hidden layer, and then we have the visible layer. And we would have an X1, X2, X3. And these are all connected with these weights. So we can have a fully connected model. We can also have connections between the different nodes in the same layer. Now that makes a more complex model. When we only have connections between the layers, then this is normally called a reduced Boltzmann machine. And then we have the X3 here, which connects with all the hidden nodes here. So in this specific case, we would have 4 times 3 weights, 12 parameters in total in the weight matrix, which connect the input layer with the hidden layer. And then we would have 3 biases for the visible layer and 3 biases for the hidden layer, no, 4 biases for the hidden layer. So this would be a typical example of such a probability distribution, which we now could think of modeling. And you can then decide whether you want this to be given by a binary model. So you could think of X taking only binary values. So you're now free to model things here. So X could be binary, could be a discrete set of events, a discrete variable. So we could have a binary value. So that means 1 or 0, -1 or +1, or continuous. So we could think of X being represented by a Gaussian distribution. And the same applies to H. So we could think of H being represented by discrete values, like a binary set of values, the 0, 1, -1, +1, true, false, etc. Same with H. And that means that we could then have what is normally called a binary model. So binary input and binary visible layer. We could have a Gaussian. That's also possible if we want that. Gaussian binary, Gaussian, etc., etc. So the type of ways of describing these data sets is almost unlimited. Now, what's going to limit us is our capability to calculate these derivatives of the cost function with respect to the weights and biases in an efficient way. But the thing now is that we have a probability model where we have parameters which we then can model with a neural network approach. So the model which you see here, this one, is normally called a restricted Boltzmann machine. So it's going to use this Boltzmann distribution, this P of x, which is now given by the exponential of minus e as a function of x. This is the input, and then divided by c. Now the input can change, so these are normally called generative models. So generative comes from the fact that you can actually generate new inputs, and these values being allowed to change means also that these are typical examples of what we normally call unsupervised learning methods. Now the Boltzmann machine, which we have met here, so the first step here, is one of the topics which we are going to look at. So after we've gone through the Boltzmann machines, we are going to look at what are called variational autoencoders, AEs, and these are based by a similar probability distribution way of thinking. And then we're also going to look at a topic which is called GANs, or generalized adversarial networks. Adversarial networks. In order to develop our understanding for these models, we need this kind of probabilistic approach, which will be based on Markov-Chain Monte Carlo simulations. So the Markov-Chain Monte Carlo simulations are needed in order to be able to simulate these probability distributions. So Markov-Chain Monte Carlo is the way we will sample these different events. Different variables or events, X and H. And we need also a rule for accepting which samples we will accept or reject. So that means that we also need sampling rules, whether we accept or reject a suggested move. And these sampling rules are given by two central algorithms in this type of Monte Carlo Markov-Chain simulations. One, which is pretty simple, is called Gibbs sampling, which we will cover. And then we also have Metropolis-Hastings samplings, which is actually the algorithm which I normally prefer and which I typically tend to implement. But it's a little bit more time consuming than Gibbs sampling. So Metropolis-Hastings sampling is one of the other central sampling algorithms. So these two algorithms which you see here, these are algorithms in a Markov chain which decide whether you will accept or reject a suggested move. So when we are simulating such a neural network like this one, we are now going to propose via Markov Monte Carlo chain simulation, we are going to propose suggested moves, and then we need an algorithm to accept or reject these suggested moves. So that's where the sampling methods like Gibbs sampling and Metropolis-Hastings samplings come in. So the overarching machinery is going to be described by a Markov-Chain Monte Carlo. So that's going to be the central method by which we are going to select stochastic events to simulate these distributions. And then the distributions are going to be simulated by these energy-based models. Now, in the optimization, however, as some of you may be familiar with, so for the optimization, it's not convenient to calculate the probability, optimize the probability, but it's actually more convenient to optimize a function which is either convex or concave. And one of the functions which then is typical to simulate from is actually to take the log of the probability. And the log of these probabilities defines a quantity which is much used in statistical mechanics and statistical physics, and which is called the free energy. So for the sampling, or no, for the modeling of the parameters, for modeling and optimization, and if we think of this simple Boltzmann machine which we had, optimization, we will need to optimize the parameters B, the biases, the parameter C, and the weights. So this is back to this simple model which we have up here. So if you look at this simple model, we now define this energy, which is a function we have chosen based on the type of data which we have. We need then to optimize this probability so that we get the best reproduction of the data which we want to represent. And we need to optimize that in terms of these parameters B, C, and W. So these are the parameters. And then, as some of you may remember from studies of, let's say, ridge regression or lasso regression or even standard linear regression, the way we can optimize the parameters when we take the product of different probabilities, instead of optimizing and taking the derivative of the probability, we take the derivative of the log of the probabilities, because that gives us either a clearly concave function or a convex function. So it's common then in the optimization to define the log of the probability, and this is normally called the free energy. And I'm going to write this as a function f of x, and it's normally given by the negative log. So this is going to be a function which will be optimized and is a concave function. And we will now be summing over something which is called the latent variables. So we are going to call this an xp. And when we look at this energy here, which we are calculating, it will depend on x, but it would also depend on these hidden variables which we have defined. So what we're doing now is that we are summing away one of the variables, the hidden variables, which we actually don't need, because we are only interested in the so-called visible variables. So this is the typical function which we will end up optimizing. And when we encounter our first examples of these type of models, which are the Boltzmann machines, so we are going to look at restricted Boltzmann machines as one type of models. So we are going to shorten that one to an RBM. So these are the type of models which we will be looking at, and then GANs, variational autoencoders, and restricted Boltzmann machines. And the first model which we're going to encounter are actually the Boltzmann machines. And they will lay the foundation for moving over to variational autoencoders and to generalized adversarial networks. So this is a kind of bird's view of what is coming now. So to remind you of the kind of overarching view, which we are going to try to digest and represent in terms of different technicalities. We are going to be in a situation now where we have so-called undirected graphs. So there's not a clear connection between the events at T0, T1, and T2. So this is normally represented by an undirected graphs. These kind of simulation situations are going to be simulated with Markov-Chain Monte Carlo methods. This leads to us introducing a probability model. And this probability model is going to be based on similarities with statistical mechanics models and then the Boltzmann distribution. And where this function E, which we have here, is now going to be represented by some parameters. It's normally called an energy. since it's inspired by statistical mechanics. But in our case, it doesn't link with a physical energy, but we will keep this kind of naming. And the probability distribution, which we will model with different parameters, B, C, and W as an example, they will then be optimized by taking the log of this function and then requiring, obviously, that the gradient has to be 0. Now, one of the problems which you already see, and which is a big issue in this type of modeling, is actually the modeling of the normalization factor. And that is going to be something which we will cover after the Easter break. Now, the thing which we are now going to look at are the Monte Carlo Markov chain approach. And that will lead us to 2 sampling rules, which is the Gibbs sampling and the Metropolis Hastings sampling. And furthermore, we need, before we move on now, to remind ourselves of some basic statistics, in particular, the link with Bayesian statistics, which we will look at in more detail after the Easter break. But now the focus is going to be on, after the break, here, today, not the Easter break, but the present break. The basic modeling which we are going to look at is a Markov-Chain Monte Carlo sampling, which then contains sampling rules like a Gibbs sampling or the Metropolis Hastings samplings. So these are the standard basic methods by which we accept or reject a suggested move in a Markov Monte Carlo chain. So Markov Monte Carlo chain samplings is also the kind of sampling method which saved the day for Bayesian statistics. So Bayesian statistics, before it was linked with the Monte Carlo Markov chain sampling, was basically a totally inefficient and void of practical interest method. And the reason for that is that the type of calculations which were done were calculations where you could calculate analytically the posterior distribution based on 2 previous distributions, which are called the prior distribution and the likelihood. And in order to be able to do anything, then you had to be able to calculate this analytically. Nowadays, with Monte Carlo Markov chain sampling, you can actually run tons of such simulations and produce a final distribution. So Monte Carlo Markov chain sampling is the kind of overarching algorithm for generating events. And it's used both in this kind of deep learning methods, which deal with GANs or autoencoders, variational autoencoders or Boltzmann machines, but it's also using as a foundation for performing Bayesian statistic and Bayesian optimization. So this was about the overarching view on what is going to come for the rest of the semester. And after the break now, we are going to dive into the details and remind ourselves first about Bayesian statistics and Bayes' rule. And then we are going to move over to the mathematics of Monte Carlo Markov chain sampling, which is going to be the basic methods for generating events. So I will stop the recording now and we take a small break. So to remind you of what is coming now, so we are going to look first at the model which is called a restricted Boltzmann machine, because that contains many of the basic elements which we need in order to study variational autoencoders and also generalized adversarial networks. So since we are going to make a statistical sampling, we need a probability distribution. And the probability distribution which we then use is the Boltzmann distribution, which is a famous distribution. And we are going to encounter that and look at this in more detail after the Easter break. And then in order to be able to sample from a given model, and the model is now represented by the Boltzmann distribution with this energy function, E, which you have in the exponential as an argument. And this energy function being inspired by concepts from statistical physics is going to be written out in terms of different parameters, the biases and the weights, And these are the parameters we want to optimize when we are setting up a neural network. To generate the different events, we are going to use the theory of Markov chains and Monte Carlo, which means that we will sample events. And in order to accept or reject the suggested samples or moves in a Markov chain, as they're normally called, we are going to use two sampling rules, either Gibbs sampling or Metropolis-Hastings sampling. These are two famous methods which allow us to reject or accept a suggested move in a Markov chain. And then for the modeling and the optimization, since the probabilities themselves, if we want to take the gradients of them, this often leads to less practical mathematical expressions. And then it's common to take the log of the probability, and that defines a concept which is borrowed from statistical mechanics, which is called the free energy. And this free energy is one of these quantities which we are going to look at after the break and how we can optimize that one. Now, however, in order to get started with many of the technicalities, we need to remind ourselves of some basics of statistics, and that will allow us to revisit Bayes' theorem, which we will also encounter later, but which we will also use in the setup of a Boltzmann machine. And then with Bayesian statistics, we are again going to move over to Monte Carlo Markov chain sampling and the basics of that. And with those ingredients, we have the theoretical background which is needed when we are going to dive into the setup of a restricted Boltzmann machine. So let's take a look at some of these technicalities using the Jupyter notebook for this week. So if you go back to the notebook, or if you just prefer to look at the standard slides, what we have here is a material on basically on a little bit probabilistic models and Bayesian statistics. And a central theorem in statistics is Bayes' theorem, which we will encounter in connection with Gaussian processes and Bayesian statistics. And this theorem plays basically the same role as Pythagoras does in geometry. And it's very simple to derive. However, there are some basic elements from statistics which we need to revisit, because these elements are elements which we will need when we are going to derive the mathematical expressions to program for a restricted Boltzmann machine as well, or when we are looking at variational autoencoders, just to look at an example. So there are some quantities here which you may have met before, and we typically deal with something like the union of events. We have defined a likelihood for x and y given by p of x and p of y. And the likelihood of a specific event, x of I or y of I, is then typically written as you can see here, or just p of I here. So the union of these events is normally given then by the probability p of x plus the probability p of y minus the non-union of x and y. And then we have something which is called a product rule in statistics. So this is just a quick review of some important statistical concepts which are needed typically to derive also Bayes' theorem. So we would then have the product rule, which is then given in terms of these different probabilities, where this px bar of y means the probability of x given y. And if you think back to these directed graphs, which we discussed before the break, that was, there we saw examples on how we use this in the directed graphs. We had the probability of a specific event T1 given an event T0. And we indicate this with this bar here. So this stands for the probability of x given y. So these two are represent the same probability. And if these are independent and identically distributed events, we could typically, if they are independent, we would typically write them out like this, where P now and identically distributed, where P, the little p here, is the same for X and Y. So if we have independent events, then this simply reduces to this quantity here. And then we have the marginal probability. And the marginal probability is the one which is going to be an interesting quantity for us when we are setting up this deep learning and generative deep learning models based on a probability, because we are going to integrate or sum away the degrees of freedom of the hidden variables. So that means that we will typically then run over sum or integrate away this variable y, and that leads to this specific operation here, where we have the conditional probability, which we defined here. So this px of y is, no, not the conditional probability, but the probability of x given y. And then we can rewrite this one in terms of this specific summation or integration over y of I. And then we have the conditional probability, which is now, if we follow the definition which we have here, so the conditional probability is now x given y, and that's defined in terms of the marginal probability and the standard product rule. So which we normally rewrite like this, or we can rewrite it now in terms of the probability of y given x, if this is something which is easy to calculate and we have a model for that, and this p of x here. And this is a quantity which we have in the denominator here, which is now simply a normalization constant. And that is, this one is what we also call the marginal probability. So p of y here is now the marginal probability where we sum over all the x's. So what you see here is nothing but Bayes' theorem. So Bayes' theorem is extremely simple to demonstrate, and it's based on the product rule and the marginal probabilities. And then we get the relation between the probability of finding x given y in terms of the probability of y given x multiplied with a probability p of x divided by a normalization constant. So right now, we are more going to use these quantities in the derivations of the equations needed for a Boltzmann machine. And we will need the marginal probabilities and the conditional probabilities in Bayes' theorem. But they are extremely simple to derive. So Bayes' theorem, if you look at this quantity py of x, which you have here, is evaluated for, can be evaluated for the observed data. So it's in case you have an observation, and it can be viewed as a function of the parameter space represented by this x. And this function is not necessarily normalized and is normally called the likelihood function. That is this function. This function p of x is called the prior, while the function on the left-hand side is normally called the posterior probability. And when we are dealing with Bayesian statistic and Gaussian processes, we're often interested in actually finding a probability distribution for the events which we have. And from that one, we can then derive error estimates for the specific parameters of the model which we have defined. So the denominator here is nothing but a normalization factor. So there is a simple example in the slides here which deals with the illustration of Bayes' theorem. And actually, why you need Bayes' theorem, because if you're not using Bayes' theorem, that can lead to totally wrong results. So the example here is an example which I borrowed from a textbook by Ian Murphy on statistical machine learning, and you should actually have access to that one as a textbook in the GitHub folder. So you can define the sensitivity for a positive event. In case of in this case, positive event is actually possible breast cancer. When you do mammography, you define that by the variable x, and that takes a binary values with x equal 1 representing a positive event and x equals 0 being a negative event. And then we can reserve y as a classification parameter for either a negative or a positive breast cancer confirmation. So you have one thing, which is the output of the mammography, but then you have the likelihood and the possibility of having cancer or not. So that's not the same as a positive event from the mammography. So we're going to let y equal 1 represent the case of having breast cancer and y equals 0 not. So if you now assume that you have breast cancer, then the test you do in the mammography will be positive. These are just numbers which are being made up. Would be a positive with a probability of 0.8. So if you come in and you have breast cancer, the machine will then give you a test with a result +1 with a probability of 0.8. And that clearly sounds very scary, since many people may actually conclude that if the test is positive, there is actually a likelihood of 80% for having cancer. So this is, however, not correct, because the correct way of analyzing this is now simply to look at the prior probability in the population as a whole. So this is the typical percentage of people who get breast cancer. So that would be the prior probability. And now, given that the person has breast cancer or not, you need to find you need to account for the fact that the test may produce a false positive result. That's a false alarm. So let us here assume that we have you do not have breast cancer, but it gives a positive result. So we can say that's 0.1. So the machine may not be well calibrated, or it may have uncertainties, etc., etc. And we quantify these kind of uncertainties in the test result if somebody has breast cancer with just a number, 0.1. And then if we use Bayes' theorem, you can then find the posterior probability that the person has breast cancer in case of a positive test. So if you use Bayes' theorem, what we are interested in is actually the number you see here. So x is equal to 1 means that the machine gives a positive test and you do have breast cancer. So y equal 1. So what is the probability that you have breast cancer and the machine comes with a positive test, or a test which indicates that you have breast cancer? Then using Bayes' theorem, we have the original distribution in the population that breast cancer has a probability of 0.004. You multiply that with the likelihood that you have y equal to 1, and then the machine gives a positive test. So px equal 1, y equal 1. And when you do the mathematics then, and you add these different numbers, you have the normalization factor, then you get 0.031%. So that means that there's only a 3% chance of having breast cancer with a positive test. And that is much more assuring than the 80% which we looked at previously. So if you say that, if you only concentrate on this number here, you may be misguided. So this tells you how conditional probabilities and marginal probabilities are used then to define the probability you are interested in. What is the probability of having breast cancer with a positive test from a mammography? And then clearly you also have to look at the case where x is equal to 0. So this is a much more assuring number, so 3% chance of having breast cancer in case the machine comes with a positive test. So this was a quick reminder of Bayesian statistics. So what I'm going to do now is to go through some of the basics of Markov chains, Brownian motion, and the Metropolis algorithm. And later we're also going to look at what's called Gibbs sampling. So the Metropolis algorithm and the Gibbs algorithm, or Metropolis sampling and Gibbs sampling, these are two central algorithms for accepting a move in a Markov-Monte Carlo chain. So the Markov-Monte Carlo chain is the overarching algorithm, and the Metropolis test or the Gibbs test, or Metropolis sampling, Gibbs sampling, they are just algorithms which are implemented inside the Markov-Chain Monte Carlo machinery to accept or reject one suggested move. So what I want to give you now is just a quick why we do Markov chains. So often, and this is more tailored to physics, we want to study a physical system which evolves towards some kind of equilibrium with a given initial condition. So you could think yourself now dropping a drop of milk in your coffee cup. And in the beginning, the milk molecules are concentrated in a small area. And gradually, as you move on, they spread throughout the whole cup of coffee. And then you get a coffee with milk or cafe latte or cappuccino, whatever you prefer. So we start with a probability distributions, and we want to understand how the system evolves with time. So time is just one way of illustrating here. And then you want to reach a situation where after a given number of time steps, we obtain what's called a steady state. And that's the most likely state the system can be in. And then when you've reached that one, then you want to calculate observables. And these observables could be things like the mean energy, it could be the average position of the objects which are being moved, etc., etc. The problem we have to face is that the probability distribution function, or just a probability distribution if we're not dealing with continuous function, or probability densities as it's also called, is normally a multidimensional object. And this normalization factor, which we call the partition function before the break, is normally a quantity which is basically impossible to calculate. And analytical calculations from the probability which we have are not possible. And to sample directly from this one can be very difficult, even if we have an analytical expressions. And also, when we are making transitions to a new state, and this is the Markov Monte Carlo chain approach, where we have a transition probability which moves us from one stage to another one. This is a quantity which normally is not known. And the question then is, how can we actually establish whether we have reached this steady state or not? And that sounds almost impossible. Now, the basic machinery for doing this is actually the Monte Carlo Markov chain machinery. And the Brownian motion and Markov processes and the physical process of diffusion, they are tightly linked together. So a Markov process is a random walk in an abstract space, or it can be in real space or whatever, with a selected probability for making a move. And the new move is independent of the previous history of the system. And the Markov process is then used repeatedly in these Monte Carlo simulations in order to generate new random states. And this is the basic recipe we will use in the setup of a Boltzmann machine. The reason for choosing a Markov process is that when it's run for long enough time, starting with a random state, you will eventually reach the most likely state of the system. And if you're doing thermodynamics, so this is a little bit more physics-based discussion here, this means that at a certain number of Markov chains, we reach an equilibrium distribution for the system. And this actually mimics the way a real system reaches its most likely state at a given temperature of the surroundings. So there are several things which we will mention here, but we will not derive them. And one is the condition of ergodicity, which means that if you can sample long enough times, then you should be able to go through all possible configurations which the system can access. That means that even if the probability is very, very small, remember now that when we have this exponential in the Boltzmann probability distribution, the probability is never zero, but it can be infinitesimally small. The principle of ergodicity says that if you are allowed to simulate for long, long times, you should be able to go through all possible realizations of the system. So if you have 10 positions and you simulate long enough, the final position would be independent of which one of these 10 different routes you took. No, not 10 different routes, but how you visited the 10 different positions in order to reach the final position. And then there's a principle of detail balance, which we're coming back to. So the Metropolis algorithm obeys the principle of ergodicity and also detail balance. So when you do a random walk, you typically define an entity called a random walker, and whose attributes completely define the state of the system. And the state of the system can refer to any physical quantities, but it could also be not a physical realization of a specific system, but it could represent a walk in an abstract space which is needed to simulate a specific system. So this walker moves in an appropriate state space by combination of deterministic and random displacement from its previous position. And this is normally the sequence of these steps forms a chain. So we want to see a system which evolves towards this most likely state from some given initial conditions. And at the end, it should be independent of the initial conditions. The Markov chains, as I said, are intimately linked with the physical process of diffusion. And the algorithm which we are going to look at is the Metropolis algorithm. But we are also going to touch upon Gibbs sampling, which is widely used in the simulation of Boltzmann machines and neural networks, because it's actually a little bit faster than the Metropolis Hastings algorithm. The applications of these type of methods are just unlimited. I'd say any fields of science, from financial engineering to biomedical modeling. Financial engineering, Nobel Prize actually went to Black-Scholes for the simulation of a diffusion equation with stochastic, with a random term, which would be this R term, which you see here. And there are tons of applications here. So I'm going to look a little bit more at the Markov process and set up a simple example, which illustrates how a Markov chain is actually set up. So you could now think of you jumping from a position X after some jumps J. So you jump a length L here. So what you would have now is that if the distance between the two positions is equal to 1, you give this a probability of 1/2. This is a transition probability, or 0 else. So this Wij is normally called a transition probability. So what we are doing here is to define a new probability distribution at a time t equal epsilon, starting with an initial distribution at t equals 0, and multiplying with the probability of making a transition from a state j to a state I. And this is the final state. This actually defines a Markov chain. So you have a function here, which normally is unknown. We don't have an expression for that. And this is something which is left to modeling. And then we have a probability distribution. In our case, with Boltzmann machines, this probability distribution is going to be the Boltzmann distribution. So if you think of this as a kind of random walk, where you have a probability of 1/2 of jumping, if you're now in just one dimension, this will be jumping left and right. Then this probability distribution is a known quantity. But normally, this is a multi-dimensional object, and you don't know what the probability distribution looks like. Or even if you know it, it would be too complicated to use in a simulation. This actually is also the case for W here. But normally we make some assumptions about how we can simulate from that probability distribution. And you will see that with using a Markov Monte Carlo chain and also adding to this a Metropolis sampling or Git sampling, this is going to allow us to be able to perform this simulation without knowing this transition probability. So this sounds like black magic. So since these are probabilities, so this W is now represented by a matrix. And this matrix is a matrix which is called a stochastic matrix, so they have to be normalized. So we will typically require that at each time step, we have a normalized probability. So that means that this Wi, which is the probability we are targeting, and in our case, we are going to use a Boltzmann distribution for that probability. This has to be summed to 1 at each step t. And then similarly, if you think of this as a matrix, what we are doing now is that we are summing the columns, elements of the matrix, and they have to sum to 1. And there are further constraints that obviously these matrix elements have to be less than 1, and same with Wj here has to be less than 1 here. Note also that the probability of remaining when you're jumping like this in the same place is generally not 0. So if you look at this process, if we scroll down here a little bit, there is a simple example which illustrates what we are having. So what happens when you simulate for long times is actually that so this will be at a time t of n, so that contains a t of n. We are assuming now that this is independent of time, this probability. It can be made dependent on time, that's an additional complication. So what we would have then is something like an n times epsilon, that's the final time t of n. And then we are applying this distribution repeatedly. And in matrix form, what it means is that we perform this operation here n times over this step epsilon, this small step. And then at the final stage here, this n of epsilon is going to go towards a large number. And what we are going to end up with then is a probability distribution, which is going to be given by this transition probability multiplied with the transition probability itself. So it means that after a certain point, we reach the most steady state. So the probability distribution is going to be given by the most likely distribution. So let's see that. So if you perform this number of steps here. So this is a 4x4 matrix. If you diagonalize this matrix, it's going to have the largest eigenvalue equal to 1. So this is because this is defined as a stochastic matrix, and a stochastic matrix has the largest eigenvalue 1. This becomes important in the analysis of this equation which you see here when we have reached the most likely state, because we are going to get an eigenvalue problem, and it's going to converge to the most likely state, which is the state with the largest eigenvalue of this matrix W. And that's going to be it's going to define the most likely state of the system. So this W is a stochastic matrix. And a stochastic matrix, you can think of either summing along the rows, or like in this case, we have defined this to be given by the normalization factor, by the summation over the column elements. So you see now that the columns sum to 1. And if you diagonalize this matrix, you will also see that the largest eigenvalue is equal to 1. So if you choose the initial state like this is just a choice. So you could think of these 4 values here to represent different probabilities. So this could be you being in slot 1. This is the probability for being in positions 2, position 3, and position 4. And so we start in position 1 with a probability of 1. And you see that this is also properly normalized. So if you then act on this one time, what we get then is a new vector. It's a new probability. And again, you see now that we were in slot 1, but now there's a probability of only 25% of being in slot 1 after one move, a probability of 50% of being in slot 2, 0 for being in slot 3, and 25% for being in slot 4. So we have now moved into a case where we are not exactly in one of the slots, which was determined by the initial conditions, but we have a probability of being in one of these 4 slots. And then we repeat this, and we see now that these numbers change. So we are now to 20%, 32%, and here we have actually 6%, and then we have 42%. All these numbers sum up to 1. So it's still normalized, as it should be. Then, if we then continue, we reach the steady state. That means that the steady state is now defined by an eigenvalue problem, because this is a matrix acting on a vector, and this means that this is a vector or an eigenstate of this matrix W with eigenvalue equal to 1. So when convergence has been reached, what we have then is a system where we now have reached a steady state which is the largest eigenvalue of this matrix W. So the set of equations which we end up with is actually this type of equations here. And if we now look at the constraints which we have, this problem here has this as the final state. So there is an almost 25% probability of being in slot 1, a 32% of being in slot 2, 6% of being in slot 3, and a 38% of being in slot 4. So if we now look at the table here, if we look at these iterations, you will now see how these change gradually when we perform the iterations. And after some 12 iterations to 6 leading digits, we have actually reached the final value which we're interested in. So if we diagonalize this matrix which you see here, this one, diagonalize that, then we do obtain this as the eigenstate, which corresponds to the largest eigenvalue, 1. And that's the same state to which this process actually converges to. So what these different iterations stand for are just dull multiplications of that matrix on the initial vector. So I could have started with any type of initial vector. It doesn't matter. It would converge to this final state if it converges. So this is a steady state solution because the equation which you see here is now independent of time on the left-hand side and the right-hand side. So this is a definition of the steady state, which is also the same as the most likely state of the system, or what is in physics often called the equilibrium state. So steady state, equilibrium state, or most likely state are the states to which this Markov chain converges to. You can also see that there is some time which is needed. You need some time steps before you have reached this optimal state. And like in this case, it's 12 time steps. In statistics or statistical simulations, this is called the burn-in time. So the time you need before the system equilibrates. And after you have reached this steady state, this is when you will start to calculate expectation values, because then you have your most likely probability. And the most likely probability is given by this little w here. So this is just a demonstration, a practical demonstration of how a Markov chain behaves. So when we have reached equilibrium, that corresponds to the largest eigenvalue of the transition probability matrix. And this state doesn't change anymore. In practice, what is going to happen, since we are going to have systems with infinitely many degrees of freedom, is that this is going just to fluctuate around some kind of equilibrium position. And these fluctuations then will also define the uncertainties or the errors in the calculations which we make. So you can understand this from a linear algebra point of view of thinking. And this reminds us a little bit of what we discussed in terms of recurrent neural networks when we had the problem with exploding gradients. So it's actually pretty similar, the way of thinking, except that for recurrent neural networks, this was the weights, the weight function. Keep in mind also that this matrix W, in this specific case, which we have looked at here, this is a well-defined matrix. So we have just defined it. In actual calculations, we have no idea on how to define that matrix. And this is where the Metropolis tests comes to our rescue. or Gibbs sampling. So when I say test, I often mean sampling or acceptance rule. See that these are just synonyms which I will use interchangeably. Now, when we look at the examples which we put up here, so let me just go back a little bit. So if you now think of these different steps, you could now think of you acting repeatedly, where T now represents some kind of arbitrary time step. The operation of this one is something which we now could represent in terms of the state W here. We could represent that in terms of the eigenvectors of the transition probability matrix. So if we do that, what we can do then is to assume that this probability at time 0 is just given in terms of a linear expansion in terms of the eigenvectors of the stochastic matrix. This results in, when we set it up, so it's fully possible because you now have a basis, and then we can expand another function in that basis, whether that's meaningful or not. But what happens then, when you study this evolution over the number of time steps, as we call them, or the number of times we multiply this initial state with this transition probability, then we have this matrix acting on these vectors. And this matrix acts, since these are the eigenvectors, I simply get the eigenvalue to the power of t. And if you go back to what we discussed with recurrent neural networks, this was a way to try to understand the problem with exploding gradients, because we could easily have, depending on the eigenvalues here, something which becomes extremely large. So for a stochastic matrix, these eigenvalues, the largest one, is actually equal to 1. So when I perform this summation here, it's actually this largest eigenvalue. If we now have sorted the eigenvalue, so lambda 0 is the largest one, it means that in the limit t goes to infinity, it's actually going to be this lambda 0, which is the one which survives. And this shows you that this series here, which we have here, is going to converge to V0 here, because all the other eigenvalues are going to be smaller than 0, no, smaller than 1, which means again then that this series here is going to converge to V0 multiplied with lambda 0 to the power of t. And since lambda 0 is equal to 1, the largest eigenvalue, that's just 1. So we are converging, the final state here converges to alpha 0 times V0. And that's our steady state of final solution. So that tells you mathematically what is taking place in a Markov chain. So if you now look at the Markov chain here, if you recapitulate a little bit, the time development of a PDF after one time step is now given by this function here. And this is now done repeatedly. And when we do this repeatedly, what we have is a process where we are going to converge to the so-called steady state. And this is the type of equation we end up with. Now, when we suggest a move in this chain, we are going to pick randomly new positions. So this is where the random part, or the Monte Carlo part, kicks in. So if you think of this Markov chain process, which we are setting up here, every time we suggest a new move, we are now going to pick random positions. And we then need to have a rule for accepting this suggested move or not, or rejecting it. So the problem which we face is that this W, making the transition from a state J to a state I, is unknown. Then we need to make a model for it. And we are free to make a model as long as it obeys the rule of a definition for probability distributions or probability density functions, in case we have a continuous probability. So the Markov chain is one part, And then we are going to use stochastic methods, which means Monte Carlo methods, to generate new positions randomly. And when we have generated these new positions, we need to find a way whether we will accept a new position or reject a new position. And that is going to lead us into the next algorithm, which is inside the Monte Carlo Markov-Chain machinery. So you can think of the Monte Carlo Markov-Chain machinery as you suggesting, let's say, 100,000 moves. And for every such move, you need to have a rule whether you accept it or reject it. So the outer algorithm is the Markov-Chain Monte Carlo method. And inside this algorithm, you accept and reject the moves according to a specific rule. And this rule is going to be given by the sampling rule, which is either the Gibbs sampling or the Metropolis sampling. So this is something which we will discuss after the break. But now we've just laid the foundation and hopefully a basic understanding of what these Markov chains represent. And then when we have that, we need to implement a specific sampling rule. And with that, we are now ready to set up our first generative neural network based on a probability distribution like the Boltzmann distribution. So this is where we're going to stop today. So after the break, we will start with the Metropolis and Gibbs sampling, and then move on to the construction of a Boltzmann machine, where we use Markov-Chain Monte Carlo and specific selection rules, which allow us then to simulate Monte Carlo Markov chain, and then find the optimal weights and biases of the model. And this is where we stop today.